afternoon, or good evening, wherever you are. Today we're going to be talking about the chemistry of life. The book that I'll be referencing is this one. This is Campbell AP Biology, and the chemistry of life is chapter 2 in this textbook. Okay, so let me just go ahead and minimize myself so that we can take a look at the PowerPoint. This is the PowerPoint that I go over in class with my students. And so the chemistry of life. And something that we need to talk about is like, why are we studying chemistry? Why is there a whole chapter devoted to chemistry? Well, first of all, chemistry is the foundation of biology. When we're studying living things, all living things are made up of matter, atoms, molecules. And so we have to study the nature of chemistry, the nature of atoms and molecules, etc. For example, like chapter 3 is all about water. Okay, water is not a living thing, but it is essential. It's an essential molecule for life existing on our planet. All right, so everything is made up of matter. Okay, matter is anything that takes up space or has mass, such as atoms. Okay, matter is made up of atoms, and atoms have protons, which are positively charged, and these protons are found in the center of atoms, and also neutrons, which are neutral, and then you have electrons, which are negatively charged. Okay, so let me grab my pen, and I apologize, I'm kind of rusty in terms of recording and stuff like that. So like, for example, here's a proton in the middle, and then you have protons and neutrons, and then you have electrons that are rotating around the outside of the nucleus. We have a hydrogen atom. Hydrogen atoms are the most simple type of element. They have just one proton in the middle of the atom, and then they have one electron that rotates around that proton. Okay, and then you have oxygen. Oxygen has 8 protons, 8 neutrons in the middle, and then 8 electrons on the outside. I like this picture. You are living, you occupy space, you have mass, you matter, right? That's the definition of matter. So what are isotopes? Isotopes are basically different variations of an element. Most elements, there's 92 naturally occurring elements. Most elements have different variations of themselves, and they're called isotopes. Like, for example, there's a few different kinds of carbon. There's carbon 12, there's carbon 13, and carbon 14. So those are isotopes. Hydrogen also has 3 different variations. There's hydrogen 0, there's hydrogen 1, there's hydrogen 2. So most elements have variations. 99% of carbon atoms that are found on our planet have 6 neutrons and 6 protons, and we call that carbon 12. And the reason why we call it carbon 12 is because 12 is the atomic mass number. The atomic mass is basically the number of protons plus the number of neutrons, and in this case we have 6 protons plus 6 neutrons, which makes 12. Okay, and so that 6 is the atomic number, which references the number of protons. So another isotope of carbon is carbon 13. Okay, so carbon 13 has 6 protons, and it has 7 neutrons, which gives it an atomic mass number of 13. So that's why it's called carbon 13, because the atomic mass is different. Okay, carbon 14, you've probably heard of this before because it's used in carbon dating of fossils. Carbon 14 is very unstable, and it's a radioactive isotope. So isotopes that are radioactive are unstable. Okay, and I'll go over that in just a minute, what that means. But carbon 14 has an atomic mass number of 14. That means it has 6 protons, okay? And then it has 8 neutrons, which gives you an atomic mass number of 14, okay? And like I said, it's unstable. So what happens is that carbon 14, it doesn't stay as carbon 14 forever, okay? It actually is going to decay and turn into nitrogen 14. So the extra neutrons here, the extra neutrons that are part of carbon 14, they become protons, okay, and they become nitrogen because nitrogen has 7 protons. So some of the neutrons become protons. So, what do we use radioactive isotopes for? In medicine specifically, we can use it for PET scans because when people take in some of this dye containing radioactive isotopes, it can actually target tumors, and it can show in a PET scan like where tumors are found in the body. So that's just like one of the uses of isotopes. So here's a periodic table, the periodic table of elements, different kinds of atoms make up the different elements. And like I said, there's 92 naturally occurring elements on our planet. That last one is uranium down here, okay? The most simple type of element is hydrogen. And then the second most simple is helium. Then you have lithium, beryllium, boron. 6 is carbon, 7 is nitrogen, 8 is oxygen, 9 is fluorine, etc. Okay? And so when we talk about living things, the 92 elements don't make up all living things. There's actually just about 25. There's about 25 elements that make up your body, that make up living things. And the majority of your cells are made up of carbon. So we want to highlight carbon here. And hydrogen, and oxygen, and nitrogen, phosphorus, and sulfur, okay? So one way to remember these 6 elements that make up most of living things is chanops, okay? So chanops, chanops, okay? Or you could do the NOPS if you want. And then you have a little, of course, you're gonna need some sodium, okay? Sodium ions are going to help regulate a lot of things in your cells, okay? We'll talk about that in a different chapter. Potassium ions, magnesium ions, and calcium ions. Those are also necessary. I'm gonna skip this slide for now, okay? All right, so life requires about 25 chemical elements. They are essential for life, but 4 elements make up 96% of living things, and that would be carbon, hydrogen, oxygen, nitrogen, and then also the other 2 that makes up a big chunk of our cells is the phosphorus and the sulfur, okay? We also have the calcium, sulfur, and potassium. Trace elements are elements that you need in small amounts, like minute amounts, like iodine. Okay, let me just move my head out of the way so you could see this example of someone with a goiter. Okay, so someone with an iodine deficiency, your thyroid glands, which are just found right over here, okay, just below your neck. The thyroid gland, it's responsible for producing the thyroxine hormones. And the thyroxine hormones are called T3, T4. They require iodine atoms. They're extremely important. These hormones are extremely important for your metabolism and growth, okay? And so if you don't have iodine in your diet, then the thyroid gland is going to swell up, and they're called goiters at that point. So when they swell up, we call them goiters. Iodine can be found in iodized salt. So when you go to the supermarket, salt is oftentimes supplemented with iodine. Or if you eat seafood, seafood is a natural source of iodine. Next slide. Okay, let's talk about bonds. So what causes an atom to make a bond? Well, going back to the periodic table, you have 92 naturally occurring elements, right? Most of those elements, most of the atoms of those elements are not alone. They're not stable by themselves. Oftentimes atoms will bond with other atoms, okay? So when we say bond, they're together, okay? And we're going to talk about like different kinds of bonds, but the reason why atoms form bonds with other atoms is because of the electrons. It comes down to the electrons, okay? Electrons are responsible for atoms bonding. Electrons determine the chemical behavior of atoms. And the majority of those elements on that periodic table, they form bonds. They're not found alone, okay? So the chemical behavior of these elements, it really depends on the number of electrons in the atom's outermost shell. Okay, the outermost shell. So in this example here, you can see that the outermost shell has 8, okay, has 8 electrons. And those 8 electrons, they're called the valence electrons because they're on the valence shell. So valence means the outermost, okay? So outer shell refers to the outer shell where the valence electrons can be found, okay? So how does this atom behave? That's what it says behind me. How does this atom behave? Because there's 8, it's going to be stable. And so actually this atom is not going to form a bond, okay? Because 8 is the number, okay? It's the magic number, okay? It's a magic number. 8 is a magic number. If an atom has 8 electrons on the outside, then it's going to be stable, okay? So chemical behavior of an atom depends on the number of electrons in its valence shell. So this atom right here has 6. 1, 2, 3, 4, 5, 6 on the outer shell. It's not stable because the magic number is 8. It's not stable, so it's going to form bonds with other atoms to become stable. Same with this atom right here. It has 2 electrons in the outermost energy level, the valence shell. The valence number is 2. It has 2 electrons, and so it is also unstable, and it's going to form a bond with another atom to become stable. Okay, so the magic number is 8 in order for an atom to become stable. All right, so atoms will react to have a filled valence shell. That's what I was referencing earlier, okay? This tendency drives chemical reactions. So in this example here, this is a lithium atom. A lithium atom has 3 electrons total, okay? The first 2 electrons are on the first energy level, and then the third electron is on the second energy level. Remember, the magic number is 8, and because it does not have 8 electrons on the outermost energy level, it's unstable. Okay, and then this is lithium Li, and then this is fluorine. Okay, fluorine is also unstable. It has 7, not 8. It has 7 valence electrons. So the thing about lithium and fluorine, though, is that they're kind of like a match made in. They're a perfect match made in heaven. Okay, lithium, it wants to become stable. Fluorine wants to become stable, but they're a perfect match because lithium can satisfy fluorine's need, because what happens is that when lithium loses this electron, and you can see this arrow, it's giving the electron to fluorine, then what happens is that now the next energy level is filled, okay? And I know I said that the magic number is 8, but in this case, the first energy level is pretty small, okay? The first energy level is pretty small. It can only hold 2 electrons. And because it can only hold 2 electrons, it's filled, okay? And so if lithium gives that third electron away, then it only has 2 electrons left, and it has a filled energy level, and it is satisfied, it's stable, okay? But it's lost an electron. Remember, electrons are negatively charged. They have a negative charge. If it loses a negative charge, lithium itself becomes an ion, okay? It becomes an ion, and when it becomes an ion, it becomes a positive ion. It's a positively charged ion, okay? It's a positively charged ion because it's lost negative charge. It becomes the opposite of what it loses, okay? So it loses that negativity and it becomes positive. Think of it that way. So lithium now has a positive charge, and we call that a cation. Sorry, I almost forgot there. A cation, okay? A cation. We call it a cation. One way to remember this is like the T looks like a positive sign. So that's how you can kind of remember what cation means, is that there's a T in the middle and it's got that like the positive symbol, okay? Whereas now look at fluorine, okay? Fluorine gains a negative charge. So when it gains that electron, now you can see it has 8. It has 8 electrons on the outermost energy level. And so it is stable, it's filled, okay? but it's gained a negative charge. So what type of charge do you think this fluorine atom is going to have? It's gained a negative charge, so it's going to have a -1 charge, okay? And so this is now what we call an ion, a negative ion, and we call that an anion. Okay, an anion. An anion. So we have cations, which are positive, anions, which are negative. So how is this a bond? How is this a bond? It's a bond of opposite attraction. Okay, so we're going to be talking about this. This is what we call an ionic bond. Later on, we'll be talking about an ionic bond. An ionic bond, okay, ionic bond is a bond of attraction. Okay, opposite charges attract. If you got a positive lithium, okay, it's attracted to, okay, the negative fluorine ion. They're attracted to each other. And so when they're attracted to each other, they come together, they get close together. Okay, they get close together. But you know what? This bond of attraction is pretty weak. Okay, ionic bonds are considered to be weak because let's say that a positively charged another, cation comes along, like maybe sodium ion comes along, then the fluorine's going to be attracted to the sodium, and the sodium's going to be... So, ions are weak attractive bonds, okay? So I kind of like this little cartoon. Like, there's an atom there saying, I lost an electron. And then the other atom says, are you positive? Because remember, if these atoms lose an electron, they become positively charged. Anyway. Okay, and so elements and their valence shells. So when you look at the periodic table, elements in the same row have the same number of shells. Okay, so like if you look at the second row on the periodic table, you'll see that lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon, they all have like 2 electron levels or shells. And then when you go from left to right, you'll see that there's an addition, a sequential addition of electrons and protons. Like for example, the lithium, let me just get my pen again, okay? For example, lithium has 3 electrons, you can see that as dots, and then it also has 3 protons, okay? And then beryllium has 4 electrons, it has 4 protons. Boron has 5 protons. Carbon has 6 protons. Nitrogen has 7 protons, etc. So as you go from left to right, you're going to see sequential addition of protons and electrons. Elements in the same column have the same valence and similar chemical properties. And that kind of makes sense too, right? Because if they have the same valence number, remember how we said that the chemical behavior of atoms depends on the electrons? Well, look at hydrogen, lithium, and sodium. They all 3 have a valence of 1. And same with beryllium and magnesium. They're in the same column. They both have 2 valence electrons. Boron has 3, aluminum has 3. So the column, they have the same valence and therefore have similar chemical properties. Take a look at helium, neon. Okay, I gotta move myself here. Take a look at helium, neon, and argon. They have a filled valence shell. And so are they going to be reactive? No, they're not going to be reactive. These guys, okay, this column is referred to as the noble gases. Noble, okay? I like to call them the loner gases because these are the only elements on the periodic table where you can find them alone. They're non-reactive because their valence shell is filled, okay? So they don't need to share electrons. They don't need to gain electrons. They're happy as they are, okay? So these are the noble gases, or what I call the loner gases, because they like to be alone. All right, moving on here. Okay, So now let's move on to bonds in biology. Okay, I mentioned how ionic bonds are weak. Other bonds that are weak, you have hydrogen bonds, and we're going to be focusing on that a lot in chapter 3, the next chapter. Okay, basically hydrogen bonds are attractions, and they're called hydrogen bonds because the hydrogen is going to have a positive charge, and it's going to be attracted to a negatively charged atom. Okay, and in this case you have water, and chapter 3 is all about water. The hydrogens in the water are positively charged, and they're attracted to things that are negative. Okay, that's why it's called the hydrogen bond. And again, a bond of attraction is always a weak bond. Okay, and so I had some technical difficulties there, so I had to start. Okay, so anyways, as I was saying, let me just okay, so hydrogen bonds are just weak bonds, attraction between a positively charged hydrogen on a molecule with a negatively charged atom. Okay, so when you look at this diagram, you can see here that the water molecule, so these are two water molecules, the water molecule H2O, right? This hydrogen has a positive charge, and it's going to be attracted to this negatively charged oxygen atom on a separate water molecule. So it's a weak bond. Okay, and then there's also hydrophobic and hydrophilic interactions. It's a type of weak bond where things that are afraid of water, that's hydrophobic, right? Because hydro refers to water, phobic refers to phobia, you're afraid of. And so things that are afraid of water, they're not going to interact with water. Okay, they're going to repel. So like oil. So oil will tend to clump together. So that association where oil clumps together when like mixed with water, oil will clump together. Like salad dressing, like if you have like a vinaigrette, right? The vinegar is mostly water. It's hydrophilic. It can, the vinegar mixture is mostly water. It can, mix with water. So hydrophilic means water and philic means attraction. So these are substances that can mix with water, like vinegar and water. But hydrophobic would be the oil part of salad dressing. They clump together. So hydrophobic interactions, hydrophilic interactions, those are kind of weak interactions, okay? They're considered to be under bonds, but they're not really bonds. They're just more like, clumping together and interacting with each other, mixing together, I should say. Next is van der Waals forces. So in your textbook, there's a really cute photo of a gecko. So like geckos are really good at climbing walls, right? How is that? It's because the surface of their, feet, okay, have a lot of surface area. And so in van der Waals, when you look at molecules with van der Waals forces, let me just draw like, you have an atom with like protons and neutrons, okay? And then you have electrons that are like rotating around on the outside. Well, if you have electrons like rotating around on the outside, at some time, like at some millisecond, perhaps the electrons are both on this side of the atom. Let me just erase, So let me just erase this. Oh, I can't do that. Okay, so let's just say that perhaps the electrons all happen to be on this side of the atom. That means that this atom is going to have a negative charge on this side, and then this side of the atom is going to temporarily have a positive charge. And that negative charge is going to be attracted to something else that's positive, like another atom that's positively charged on this side. So van der Waals is an attractive bond, okay, attractive force between molecules and atoms with temporary positive and negative charges, okay? And that can happen quite often when there's a lot of surface area, because there's a lot of surface area, therefore a lot of molecules with a lot of van der Waals forces, okay? And then ionic bonds, which I talked about earlier, they're very weak bonds of attraction. And then, so strong bonds, the only strong bonds that we're going to talk about is covalent. Okay, I don't know if you guys can see that there, but it says on the bottom of my page, covalent bonds, and we'll go into detail of covalent bonds. Okay, so, I like this diagram because it does a better job of explaining what van der Waals forces are, okay? So if you have atom 1 here with electrons on the outside and atom 2 with electrons on the outside, a split second in time, okay? The electrons happen to be on one side of the atom, leaving this side of the atom negatively charged, this side positively charged. Therefore, it's going to be attracted to another atom that might have negative charge on this side and a positive charge on this side. Remember, opposite charges attract? So if you have a negative charge here and a positive charge here, then there's going to be an attractive force, okay? So that's van der Waals forces. Now let's talk about covalent bonds. Why are covalent bonds so strong? Okay, it's because atoms are sharing electrons. Okay, remember ionic bonds are weak because it's a bond of attraction, whereas with covalent bonds the atoms are literally, they're overlapping. Like the valence shells are overlapping and they're actually sharing the electrons together. So both atoms are holding on to the electrons. And covalent bonds are very stable. It's very difficult to break apart a molecule that's held together by covalent bonds. So molecules are formed in covalent bonds. So you can see here that these two, and these are two hydrogen atoms, these two hydrogen atoms are sharing these two electrons. And so the energy levels, the valence shells, are overlapping. They're really close, and they're held together close because they're sharing those electrons. Okay? Those are two hydrogen atoms. Oh, and we like to represent, like, for example, let me just draw like methane. Okay, methane is CH4. It is a molecule made up of two elements, carbon and hydrogen, and it has one carbon. It has 4 hydrogen atoms, and they're held together by, this is a molecule that's held by a covalent bond. And we like to show lines that represent covalent bonds. So here's a carbon that's covalently bonded with this hydrogen, and then it's covalently bonded to this hydrogen, and it's covalently bonded to this hydrogen, and it's covalently bonded to this hydrogen. So this carbon in the middle is sharing electrons with 4 hydrogen atoms. It's a very stable molecule. Okay, that's methane. And so methane is a molecule made up of 1 carbon and 4 hydrogen atoms, and that carbon is sharing electrons with 4 different hydrogens. Okay, same with water, and we'll talk more about water in chapter 3, but water is H2O, and it's 2 hydrogens and 1 oxygen, and they're sharing electrons. So, you know, I drew methane gas, methane, which is the hydrogen, 4 hydrogens sharing electrons with carbon, but you can also have atoms sharing 2 pairs of electrons or 3 pairs of electrons. And in that case, we call them double bonds or triple bonds. And those bonds are very strong. Double bonds and triple bonds are extremely strong because they're sharing more electrons, and it would be more difficult to pull them apart. So they're very strong bonds. Oh, okay. So yeah, there's methane, and it got cut off at the bottom. But anyways, yeah, the more bonds, the better, because it makes it more stable. Okay. So when when carbon is formed, it forms a non-polar covalent bond because that carbon in the middle is sharing electrons with 4 hydrogen atoms equally. So the electrons are being shared equally. Okay. Methane was our example. So when they are equal, when the electrons are being equally shared, it's balanced, it's stable, and hydrocarbons are good examples of this stable covalent bonding that occurs between carbon and hydrogen, and it's a good building block because it's very stable. When I say it's stable, it's not going to it's not going to be reactive. It's not going to react and become something else. It's going to stay as a hydrocarbon for a very, very long time, unless there's some kind of chemical reaction where we're using enzymes that are going to break it apart. Okay, so that's the non-polar covalent bond. It's very stable. Whereas polar covalent bonds are where their atoms are unequally, where they're sharing electrons unequally, okay? So this is where a pair of electrons share unequally by two atoms, okay? So water is a really good example, okay? And again, chapter 3 is all about water, but let's talk about it. Let's get a sneak peek, okay? Oxygen. So oxygen needs to share electrons with, it needs to share, it needs two more, sorry. It needs two more electrons to become stable because its valence shell is 6, okay? And so when it shares electrons with other atoms, it shares it unequally because oxygen is electronegative, okay? Oxygen is extremely electronegative. And what do I mean by that? It attracts the electrons that it's sharing closer to its nucleus, okay? You can think of electronegativity as being kind of like selfish. Like when it shares, it selfishly pulls the electrons closer to it, okay? And it has to do with the 8 protons in the middle. There's like 8 protons, and protons are positively charged. So that's a lot of protons that are in the middle. And so when it shares these electrons with hydrogen, and think about it, hydrogen has how many protons? It only has 1. So it only has 1 single positive charge in the middle, and these electrons are negatively charged. And so opposite charges attract. Those negatively charged electrons are going to be weakly attracted to that single proton, that single positive charge in the center of the hydrogen atom. Whereas a oxygen atom has 8. There's 8. So there's a big pull of those electrons towards the 8 protons, the 8 positively charged protons in the center of the oxygen atom. So that's what electronegativity is referring to. It refers to the pull of the electrons towards the nucleus, and oxygen is very, very electronegative. And so as a result, water is a polar molecule. It's a polar molecule because it's has a charge, okay, has a partial positive charge by the hydrogens, and then a negative charge by the oxygen, okay? Negative charge by the oxygen because the electrons are being pulled towards that nucleus of the oxygen. So polar covalent bonds is sharing of these electrons, but it's unequal sharing, okay? It's unequal sharing because the electrons are going to be pulled closer towards the oxygen. They're going to spend more time with the oxygen than the hydrogen. So it leads to a polar molecule. Anytime there's a polar covalent bond, it makes the molecule polar, okay? Polar. Think of it this way, like when you think of polar, think of like North Pole, South Pole. The Earth has the North Pole, South Pole, opposite ends, okay? Water is a polar molecule. It has opposite ends. It has a negative end and it has a positive end. Think of it that way, okay? So that's what I mean by polar. It's going to have like opposite charges on opposite ends, okay? All right. And again, the polarity of water, we're going to talk about in a lot of detail in chapter 3. All right. So hydrogen bonding, I said, is the weak attraction between a positively charged hydrogen in one water molecule to the negatively charged oxygen in another water molecule. So, you know, water again is made by polar covalent bonds. Water is a polar molecule. Water is positive charged on the hydrogens, negatively charged on the oxygens. Therefore, the positively charged hydrogens on one water molecule is attracted to the negative charge on another water molecule, the oxygen of another water molecule. And that's a weak hydrogen bond. Okay, it's a weak bond. Okay, the last part of chapter 2 is the law of conservation of mass. Basically, this states that, you know, mass cannot be made spontaneously. Mass cannot be broken and lost. Okay, chemical reactions make and break chemical bonds, and you have to have an equal number of atoms or mass, okay, in the reactants and in the products. So the reactants, these are the molecules that the reaction starts with, reactants. the reaction starts with. And then you have the products. The products is what you end up with after the chemical reaction. And so when you count the number of atoms on the reactant side of a reaction, they have to equal the number of atoms in the product side. So what I'm going to do is I'm going to count the number of hydrogen atoms on this side. Hydrogen, there's only 2. On this side, there's 2 oxygens. On this side, in the products, we have 2 hydrogens, but I don't see a number 2 after the oxygen. That means that there's only 1 oxygen on this side. And so, according to the law of conservation of mass, you can't just lose 1 oxygen in a chemical reaction. That oxygen needs to be accounted for, okay? So this is a chemical reaction that is unbalanced. It's not balanced, it's unbalanced. And so you have to balance this chemical reaction. And so this is something that you'll probably be doing next year in chemistry. In chemistry, you're going to do a lot of like balancing equations. But I'll just show you really quick how to do that, okay? Let me erase all the ink there. Oops. So we have the reactants, the products. Okay, so the thing that we can add to a chemical equation are what we call coefficients, okay? Coefficients are large numbers that are in front of molecules. When we add coefficient 2 here, that does balance the equation because now it's 2 times 2, I get 4 hydrogens, okay? And that 2 is not in front of the oxygen, so that means that the oxygen stays as 2, whereas 2 times 2, I have 4 hydrogens, and then 2 times 1, I have 2. So now, is it equal on both sides? Yes, it is balanced on each side, okay? And here's a visual. I need 2 hydrogen atoms, or 2 hydrogen molecules, I should say. If I have 2 molecules of hydrogen, that's 4 atoms of hydrogen, a molecule of oxygen, and then I need 2 water molecules to give me 4 hydrogen atoms and 2 oxygen atoms. So now I have it balanced, okay? All right, so that's basically what I wanted to go over. You're going to do more balancing equations when you get into chemistry, but the gist of it is like, you know, the reactant side, you have to have equal number of atoms of each element on the reactant side as the product side, and the only thing that you can do to balance it is by adding coefficients, okay? All right, so that's it with this PowerPoint. I hope that it was helpful, and let me know if you guys have any questions.